Hello, everyone. Today we are going to be covering section 8.1, which is about arc length. So arc length is just a cool application of integration. So in the previous chapter, chapter 7, we learned a bunch of integration techniques. And then now we're going to just learn one possible application of integration. So let's first talk about what arc length is. So if we're given a function, a curve or a function f, we may want to find the length of this curve between 2 points A and B. So let's say I have this curve here, let's call it f, and I want to find the length of this curve between points A and B. And there's a lot of applications to this. It might seem like, why would we bother finding these curves? But you know, this kind of stuff is done in your navigation systems for like finding most efficient routes and all that. And if you go on your GPS, you know, it tells you how far you have left to travel. That's done by things, you know, computers that are doing techniques like this. Okay, so arc length is going to tell us the length of this segment between A and B. Okay. So let's first discuss the theory of how this is done. And just like with integration, it's built up from, we're going to start by approximating the arc length, and then we're going to take the limit of that procedure and hopefully get an exact answer. So let's kind of consider this white curve, and let's say we wanted to find the arc length of that. Let's start by approximating it with these green lines. So first let's be precise. Let's say we want to find the length of the white curve between points A and B. Okay. And now let's start approximating this curve with these green line segments. Okay. Maybe the length of the white curve is hard to find, but these straight green segments, I can find the lengths of those easily. So I kind of chop this up into pieces. Okay, and I chop this up into my 3 green line segments, and then if I can figure out the lengths of those 3 green line segments, that would be an approximation to my arc length, right? So let's talk about the length of one of these green line segments. Okay, so let's look at this one, this first one here. All right, what is the length of that green line segment? Okay. Let's say my green line segment starts at point x1 and goes to point x2. Okay, so this dot is at x1, this dot is at x2. Okay. So I know this horizontal distance here is x2 minus x1. Okay. And if I know this vertical distance here, well then I can just use Pythagorean Theorem to find the length of my green line segment, right? Because it's forming a triangle here. So if I know this distance is x2 minus x1. What's this vertical distance here? Well, this is going to be y2 minus y1, which, let's see, if my curve is f of x, those y coordinates are going to be given by f of x2 and f of x1, right? So what I'm trying to say is this distance here is x2 minus x1, and this vertical distance is f of x2 minus f of x1. Okay. So now let's use the Pythagorean theorem. What would then be the length of that green line segment, right? It would be x2 minus x1 squared, right? This distance squared, plus f of x2 minus f of x1 squared. So this vertical distance squared, right? And then if I take the square root of that, that should give me the length of my green line segment. Okay. So hopefully that's clear that this would be the length of this single green line segment. And now all we're going to do is we're going to play with this top expression here. We're just going to rearrange it and to get it, and to get in order to get a form that's easier to work with. Okay, so let's first factor out x2 minus x1 from both of these. Okay, so I can write this expression, this top expression, if I factor out x2 minus x1 within the square root. Okay, I bring the square root, or I bring x2 minus x1 here, and then what would I be left with? Well, this term would become 1, and then this term would become f of x2 minus f of x1 over x2 minus x1 squared, right? So basically, maybe it'll help to see what I started with was I have a squared plus b squared, right? And I factor out the a squared, and that gives me 1 plus b squared over a squared, which is the same thing as b over a squared. So that's kind of what we've done. Okay, and then I can take this x2 minus x1 squared, I can go ahead and take that out of the square root, right? And when I do that, I lose this square term. And so it just becomes this, x2 minus x1 outside the square root. And then inside the square root, I'm left with 1 plus fx2 minus fx1 over x2 minus x1 squared. Okay. Now let's just call this distance x2 minus x1. Let's just call that delta x. Okay. Delta x being the distance between these 2 points here. And if I had x2 to x3, that would give me another delta x, and so on. Okay. Now, so what we've found is that this is the length of one of my green line segments, right? Now let's just add them all together. Okay, so we found the length of one of these green line segments. Okay, so we found the length of like this thing. Now let's go ahead and add the length of this thing and the length of this. What would that look like? Well, if I add them all together, let's say there's n line segments. What is it going to look like? It should look like this. So the sum from 1 to n of square root 1 plus f of xi plus 1 minus f of xi over xi plus 1 minus xi, all squared. Okay, so don't freak out about this too much. It's just, this is like, if I have a green line segment, these are the y coordinates and the denominators are the x coordinates. Okay, and then I've just brought my delta x here and back. I've just kind of rearranged it a little bit. Okay, now this might start to look familiar as how similar to how we built up the integral, right? So the idea is that if we take the distance between these two x coordinates to be smaller and smaller and smaller, the approximation is going to get better and better and better. All right. So maybe at one stage I have an approximation that looks like this, where I got these 3 kind of chunks. Okay. And then I take the distance between my x's to be even smaller, right? So like maybe I got chunks like this. So I chop it up into 1, 2, 3, 4, 5, 6, 7 chunks. Okay. Well, we can tell that this approximation to my arc length is going to be even better, right? And so I'm going to add more, and I'm going to make this distance between points, this horizontal distance, I'm going to make that shorter and shorter and shorter. And so I'm going to have more and more green line segments, more of these approximating line segments. In other words, I'm going to take the limit of delta x going to 0. And what happens when I take that limit going to 0? Okay, I'm going to end up with an integral, right? So remember how we built up our approximation to area and things like that, taking a limit of a sum like this. Okay, now let's examine what happens to each of the terms. The summation becomes an integral sign. We're maybe kind of used to that idea, right? This idea that the integral is kind of a limiting consequence of the summation. What happens inside the square root? think about, let's examine this term pretty closely. And forget about the square, forget about this square term for a second. Just think of f of x I plus 1 minus f of xi over xi plus 1 minus f of xi. First, ask yourself if this looks familiar, okay? And in particular, what happens when we take the limit as h goes to 0? Does that ring any bells? That should maybe remind you of the derivative, because this is exactly what the derivative is. Remember, the derivative is the limit of an expression like this. Okay. So what we have in our expression, in our approximation that we're constructing, what I had written in the summation was this. All right. So now look at this stuff inside the parentheses. Okay, and we're, in the back of our heads, we're taking the limit of this as the distance, this delta x goes to 0. Okay. Well, if delta x is going to 0, that means the limit of the distance between these points is going to 0. So in other words, we have a situation like this, where the distance between these 2 points is going to 0. Okay. So what should this become? This is just going to become f prime of x, just like in this expression up here. So what we have in our expression, this term in parentheses is going to become f prime of x, and then we're squaring it. Okay. In other words, this term becomes the derivative of f at x. It becomes f prime of x, and then we're squaring it. That this square doesn't change. Okay, so the only thing that changes is the stuff inside the parentheses. It becomes the derivative. And then as we take the limit of delta x going to 0, what happens to my delta xi? It becomes my d of x. Okay. So maybe we see that the limiting behavior of this is this. Okay. In other words, this integral is going to be the perfect approximation. It's going to give us the true value of our arc length. So to make a long story short, we get this nice formula for arc length. If I want to find the length of a curve between 2 points A and B, it's just square root of 1 plus f prime of x squared dx. Okay, so really, if you want to understand the theory, that's what I just covered. And if you just want to memorize a formula for arc length of a curve f, it's this. So we got to be able to take the derivative, and then we got to plug it into a square root, 1 plus f prime of x squared, take the square root, integrate, that'll give us the arc length. So let's see that in action. Let's do an example. Y equals 1 plus 6x to the power of 3/2 in between 0 and 1. So I want to find the arc length of this curve. Okay. So what does it look like? Maybe roughly, just doing a rough draft. Let's see, 6x to the 3/2, that would look maybe something like this. And then we're shifting it up by 1. So maybe our curve should look something like this. Okay. Just a really quick rough sketch. All right. So I want to find the length of that curve, boom, between 0 and 1. Okay. So I know from this line right here, the arc length is going to be given by 0 to 1, right? Those are just my bounds I'm given. And then I need to do the square root of 1 plus f prime of x. Well, if this is my f of x, what's f prime of x? Let's see, the derivative of this thing would be 3 over 2 times 6x to the 1/2, right? In other words, 9x to the 1/2. And then I need to square that. So what do I get when I square that? I get this. So now I need to integrate 1 plus 81x. Okay. We could do this with a u substitution, right? The rest is just basic integration, but we can go through it real quick. We would do u equals 1 plus 81x. Du equals 81 dx. So du over 81 equals dx. Plug that substitution in. Get something like this. And now plug in my bounds. Something like this. And I won't bother simplifying the answer, but that should be an answer. We could probably plug it into a calculator and find some decimals or whatever, but this should be an answer. All right, so we found our arc length. This would be our arc length. You know, it's not very simple, but that's our arc length. The process to find it though wasn't too bad, right? It's just plugging our deriving our function, plugging into our formula. Okay, so this chapter should be pretty straightforward. It's really just knowing that basic formula and then using our previous integration techniques. All right. One other thing I'll say is that we have something called the arc length function, which is just a slight extension of our idea of arc length so far. So let's say I have a curve f of x like this, and I want maybe I want to be able to find a bunch of arc lengths for this function. Maybe I want to be able to find my arc length to this b, this c, this d, e, f, and so on. Basically, I want to be able to plug in any x value I want, and I want to be able to find the arc length. Okay, so I kind of want a function. I would like a function g so that I can just plug my endpoint into g, and it's going to spit out the arc length. Okay, so that's what our arc length function is. How can I develop arc length function? Okay, g, and it's not anything super complicated. It's actually, maybe once I show it to you, it'll be kind of obvious, and you'll say, why did we even bother doing that? But I'll show it to you nonetheless. So going back to this idea, if I wanted to find the arc length here, right, from A to B, my arc length, let's call it S, S of B, or, well, since we're using the notation G, let's say G of B. Okay, my arc length up to point B would be given by this formula, right? I know it'd be equal to this formula. Right? And if I wanted to find my arc length up to C, well, it'd be very similar, except at this endpoint, this bound, I'd have C for my integral. And in general, if I want to call this a function, I can just put x here, right? And then I should have x here as well. Okay, we call this thing our arc length function? Meaning if I plug x in, if I plug some value for x into this right side of my equation, it's going to give me my arc length. So it's maybe something you're going to deal with on the homework a little bit. They might ask you to write the arc length function for some curve, something like that. But it's not anything too complicated, right? And really, that's about it for the chapter. There's maybe it mentions something like Simpson's rule or something like that, but you shouldn't need that for homework, and that's not going to be on the test. So really, what I've shown you is all you need. So pretty short section. I will do a problem video for this, but the idea is pretty simple. And really, that's all we need from section or chapter 8. So that we're just doing this one section from chapter 8, and then for the next video, I'll be moving on to chapter 10. All right. As I said, problem video to come.